Calculus BC, we are going to take a look at a new lesson involving integration. So much of what we've done this current unit has dealt with integration already. Today we're going to learn integration by parts. And integration by parts, we're learning a method, as you can read here. It's essentially reversing the product rule, but this is when we need to use it. Obviously, when we're integrating, we should always ask ourselves, is there an obvious antiderivative? Can I just simply reverse a power rule? Or, am I aware, do I recognize an antiderivative from inverse trig memorization facts that we've had? Even recognizing some of the 7.4 theorems. If that's not applicable, you might wonder if algebra could help. And if algebra with factoring, Hart rule, even completing the square as we've done with inverse tangent, if none of those are successful, you could ask yourself, well, wait a minute, would a U substitution work? Sadly, even the U substitution can fail. Here is a new method that we can use. And again, the idea is essentially this: an integral that is of this form. If you can envision an integral being able to be broken up as a u component and a dv component, then you can be rewriting it. You can rewrite that as uv minus the integral of v du. And guys, this is what you want to memorize. This is definitely what you want to memorize. If you can look at an integral in this way, you're going to have this new right-hand side that you can work with. I think I need an E right there. Oops, my pen's going a little nuts. There we go. Okay, so the trick, of course, is, well, wow, I'm looking at this integral, I'm looking at U. Here's a little guidance. To select U, we're going to look at an integral, and we're going to look inside of that. There is an acronym that we can use, LIATE, LIATE. And the L stands for logarithms, or just logs. How about that? I is for inverse trig. A is for algebraic terms, something like x to a power. Even radical x can become x to the 1/2. T is trig. And finally, we could have exponential functions. Select U following this checklist. First, see if there are any logs. Then go to inverse trig. Then go to algebra, go to trig, go to exponents. Let U be the inside of that integral. What is not selected is dv. So obviously we've got this formula here. Wow, and this can sound so different. Thankfully, this is what many calc teachers and professors will say is extremely mechanical. You wind up doing so much of the same basic steps here. So let's see this in action. Okay, we're going to come down here to example 1. And of course, we should go through our little protocol. Do I know an obvious antiderivative of x times the sine of x? And no, that nothing is going to come to mind. Nothing even in our recent lessons will jump out and say, oh yeah, we can find an antiderivative with a new formula, like inverse trig formulas that we've worked with. Could algebra be done? Sadly, no. Could I try a U substitution, letting U equal x or U equal sine of x? You could certainly try that. It just won't help. So a U substitution isn't going to help us out here. So instead, like I said, this generally is used when we're reversing the chain rule. Let's look up on the notes here, still on the screen. I'd like to select a u, and I'm going to go through my checklist. I'm going to go through Lie8. Do we have logs inside of the integral? No natural log, no log base 10, no. Inverse trig. No, I don't have inverse trig. Do I have something algebraic? Yes. That's x. Now, you could say, okay, so now I've got my u. Well, guess what? That means that there was something that was not selected. So imagine that the u was over here in yellow. What didn't you select? Well, what you didn't select was this sine of x with the dx. And watch this. I'm actually going to write sine of x dx right here. So you can think, well, my goodness, what's the plan? Here's what we're going to do. With what's been highlighted in yellow, I'm going to take my derivative. I'm going to get du, and the derivative of x with respect to x is just dx. When I have dv, I'm going to take an antiderivative. V is going to equal, it's almost like imagine that you're integrating right here. What's the antiderivative of sine? Careful now, it's negative cosine of x. Okay, so right now you can think, okay, so what's going on? Well, you just reinterpreted this problem as u dv, and let's follow what you should have memorized, or you will shortly. This integral can now be rewritten in a brand new form, uv minus the integral of v du. So I'm going to have x times opposite cosine of x. We'll clean that up in a minute. Then we'll have our v. Here's negative cosine of x. And du is just dx. Look at that. Now, I want to point something out to you very, very, very quickly, stating the obvious. We can see there's a minus and a minus right here. Well, let's get to work. The x times negative cosine of x, we have negative x cosine of x right here. Minus and a minus make a plus. You see, brand new problem where now I have such an easier integral. That's that v du. I now know the antiderivative of cosine is sine. And don't forget, you're going to have to always write your arbitrary constant, a plus c. And there you have it. Now, listen, you might be worried about this perhaps on a quiz, test, you name it, AP exam. You might be thinking, gosh, is this right? Here's the thing, guys. You can always double check if you've done this correctly by just taking a derivative. You should get back to the integrand, what is inside the integral. If you took that derivative, you will, in fact, get x sine of x. So that is actually integration by parts, a brand new method. When our previous methods fail, we've got a brand new tool. Let's take a look at example 2. So very often this one, so many students want to quickly say, what's so hard about this? It's 1 over x plus a constant. Well, that would be a derivative of natural log of x. We're asked to take an antiderivative. And if you look back on your notes very carefully all throughout our chapter 7 notes, you're going to see that never, ever did we learn of a function when you take a derivative of it, you'd get natural log of x. So, wow, no algebra is going to help. A u substitution, you don't have much choice. You could let u equal natural log of x. It's not going to help, though, is it? So we're going to hope as a last-ditch effort, because let's be honest, this is our last method of integration that we have at this point. You could say, well, is there a u? Let's go back to Lie8. Is there a log? Oh my goodness, yes. Thank goodness. And that's going to be let u be ln of x. So that's lovely, right? And you'd say, well, dv's got to be what you did not select for u. There's not much left. That's just going to be a dx. All right, well, let's go ahead. Take a derivative right here of natural log, like we said, 1 over x. Here we're going to take an antiderivative. You'd have v equals x. And by the way, we can get away with not even worrying about a plus c until the very end. Don't worry about that at this point. So we can see that this is uv minus the integral of v du. And we can say, well, what's our u? That's ln of x. Our v is just an x. Generally, we're going to like to pull that out in front. My v is an x. My du is a 1 over x. Forgive me, did you see I made a little bit of a mistake right there? It's that 1 over x dx. You can see I forgot that. Don't forget that. You need your differential here. Look at that. So look, we're going to have x ln of x minus the integral of 1 dx. And my goodness, what is the antiderivative of 1? Just an x. But then we're going to put a plus c at the very end. So let's flip over to our last page of the notes, second page, thankfully. You can think, well, wait a minute. So far, let's be honest, we've dealt with really nothing involving limits of integration, no definite integrals. Here's what you're going to notice with that. You still have uv, what you've memorized, but from the fundamental theorem here, we'd have to evaluate that from a to b. And then we'd have for right here the integral of a to b of v du. Okay, so let's real quickly take a look right here for example 3. Again, so very often students will go, oh, Mr. Dobner, this is no big deal. Example 3, oh man, I get it. It's 1 over 1 plus x squared. Because that's what a derivative of inverse tangent is. Right? That's one of those derivative formulas that we learned in 7.6. And that's not what they're asking. They're not saying, please take the derivative. They're saying, take the antiderivative. And we think, well, my goodness, what can I do? Well, obviously, we don't know an antiderivative of inverse tangent off the top of our heads. No algebra is going to be helpful. Listen, you can try a u substitution. It's just going to leave you frustrated. So let's try integration by parts. And there really isn't too much. Looking at Lie8, you could say, well, wow, no logs, but oh my goodness, inverse trig. Inverse trig right here. Look at that. So we can go ahead and take a look at this thing. And then what have we not selected? Well, I think you can see already it's that pesky little dx right there, right? So that's what dv is going to have to be. What didn't you select as your u? Well, not much left, just this right here. So let's get down to business here and hope that this is going to work. I'll have du equals, well, this is going to be 1 over 1 plus x squared dx. I'm going to remember that dx right now. And then antiderivative here, that would be v and x. And wow, this is truly a challenging question right here. A lot more work, but so good. It's so excellent to take a look at this. Look, we're going to say here's uv, evaluating that from 0 to 1, minus the integral from 0 to 1 of v du. And your u right here is inverse tangent of x. Your v right here is an x. And right now, this can get a little bit scary. You could say, wait a minute, I'm going to multiply v and du. So very often kids are like, wow, this is going to get multiplied. This thing and this thing are going to get multiplied together. That's like x over 1. Yeah. I think this form right here can get scary, where you've got x over 1 plus x squared. And of course, You could have left that as x times 1 over 1 plus x squared dx and just joined them, but end result, we're looking at that integral and maybe we're not feeling too good. Well, there's a lot more to talk about. First of all, if we did this fundamental theorem, we could say inverse tangent of 1 times a 1 minus inverse tangent of 0 times 0. Well, 0 times anything goes away. Inverse tangent, I hope you remember, had boundaries between negative pi over 2 and positive pi over 2. Wow, it's been a while since we've seen that. And you'd say, what angle would tangent have a value of 1? Very famously, that's pi over 4. So this right here just becomes pi over 4. But, my goodness, the real issue that kids get worked up on, and understandably so, is, okay, so you did integration by parts. We were able to do something. But, oh my goodness, what about this thing right here, this integral with x all over 1 plus x squared? Yeah, it's daunting that we glance at it and we don't see an obvious antiderivative. You might want to try to do some algebra here. A heart rule is not applicable. It's not an upside down heart. No algebra is going to help you out. And as you look at this, you'd say, well, what else is there? You know what? There's a U substitution for this problem. Oh my gosh. Maybe we could do a U substitution. Unlike earlier, the U substitution certainly wouldn't help. And by the way, if you'd like to, you could even use something other than U because you had used U up above. You could say call it a W substitution if you want to. U is just any variable you'd like. It's a dummy variable. dw would be 2x dx, and dx would be dw all over 2x. And let's just work this out. Down here's a w. Here's dw all over 2x. And the bounds are going to change. Look, when x equals 0, look at that. 1 plus 0 squared is what we have for w. That's just a 1. Your new lower bound is a 1. When x is equal to 1, w is 1 plus 1 squared. Hey, that's a 2. And look at that. Things are getting better. Now this integral, remember we've got our pi over 4 out in front, but you could say I'm going to pull out a 1/2. And you could say, how could I finish this up? Well, tell you what, fundamental theorem of calculus. I'm going to just say ln of w. Very often students will go, wait, you forgot the absolute value. None needed because the bounds, the limits of integration are all positive. So wow, this is a real nice challenge problem, guys. This is a real nice challenge problem. Natural log of 1 is just a 0, so that's going to go away. Final answer, pi over 4 minus 1/2 ln of 2. Look at that. All right, and now the good news. Now the wonderful, 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 exciting news. Tabular integration by parts. Tabular integration by parts can be a tool. It doesn't always work. It doesn't always work. We have to be so clear about that. But when you can use it, oh my goodness, take advantage. It is a shortcut, and you'll be able to use it a lot, thank goodness. What's going on? Well, look at example 4. Obviously, I don't know an antiderivative. Algebra is not going to help. U substitution won't help. Usually kids will go, okay, well, I guess I've got to do integration by parts. Yeah, good idea. But listen, I guess what I want to remind you of is to select U. We're going to do light. I'll say, do I have any logs? No. Inverse trig? No. Algebra? Yeah. And then that right there can be my u. Now, what did we not select? Well, we did not select the e to the x dx. That's what's going to be dv. Now, could we do our ordinary integration by parts? Yeah, but when you can't, and by the way, this would require us to do integration by parts multiple times. That would be rather upsetting. That will happen, but this is such a shortcut. With this, we're going to take derivatives. What's the derivative of x squared? Well, you'd say it's 2x. What's the derivative of 2x? A 2. What's the derivative of 2? 0. And this is where we can be very happy. Guys, when you select a u and you can eventually take derivatives of that u term and get 0, it's very possible you're going to be able to do integration by parts. But now what? Here we're going to take antiderivatives. And what's the antiderivative of e to the x? Oh, thank goodness, e to the x. What's the next one? E to the x. Keep doing antiderivatives. So when you can do both, select a u term and take consecutive derivatives and get 0. By the way, kids will say, you can always do that. Oh, no, imagine if I gave you u equals sine of x. Oh, that wouldn't work, would it? You wouldn't eventually take a derivative and go to 0. Algebraic terms, though, that's gives us a lot of hope. But that alone is not enough. You also have to be able to have your dv term taking consecutive antiderivatives. You'll be able to at least stop to where you get 0. And now what? This is language made famous in the movie Stand and Deliver, which was a movie about calculus students in Los Angeles, based on a true story. The teacher in the movie called this method tic-tac-toe because you kind of slash when you win. But what you're always going to do, start with plus, then go to minus, plus. You always alternate. And what's your final answer? This, x squared e to the x minus, you see your next one's a minus, 2x e to the x plus, now I'm going to have my plus, 2 e to the x, don't forget, end with a plus c. Oh my gosh. That gets used a lot. And best of all, the College Board will recognize this as a valid method. This is called tabular integration by parts. Let's do one last one. Again, you can see right here, we could go through our checklist and, sadly, no matter what we try in previous methods, it won't work. Do I have logs? No. Do I have inverse trigs? No. Do I have something algebraic? Yes. Yes. So what you have is something very, very hopeful. And then you could say, well, what would dv be? Well, dv would be whatever you did not select. And dv is going to be this thing right here, sine of x dx. And now what? We're going to take derivatives going down this way. 3x squared, 6x, 6, 0. Right now, I'm very hopeful that we can use integration by parts, the tabular method, because of this. But it's not enough. I have to also realize I need antiderivatives. I have to be able to find antiderivatives for all these steps. What's the antiderivative of sine? Negative cosine. What's the antiderivative of negative cosine? Negative sine. What's the antiderivative of negative sine? Cosine. And finally, what's the antiderivative of cosine? Sine. Then we'll do our tic-tac-toe. And we'll say here's a plus, minus, plus, minus. And look at that first diagonal. X to the third, negative cosine of x with a plus. Tell you what, a negative would just come out then. Look right here with your second diagonal here. You got a minus, you got a minus, a negative and a negative multiplied to a plus. That's how that works. Look at the next diagonal. I'm talking about, this one right here. That's going to be a plus 6x cosine x. Next one is going to be a minus 6 sine of x. That's your last one. And guys, look at that. Amazingly, that is tabular integration by parts.